So we are starting today by looking at Chapter 16. Chapter 16 is a focus on radioactive materials. And so like I said, chapters 4 and 5 were the last really chemistry intensive chapters of the entire semester. And now we're getting into more thorough breakdowns of individual classes of hazardous materials, starting with the radioactive materials here. And when it comes to nuclear and radioactive materials, there are some regulatory agencies at play here. First and foremost, Nuclear Regulatory Commission, the NRC, is responsible for the licensing and the oversight for any facility that uses any kind of material that has an intense radioactivity to it. They're the ones that are ultimately responsible also for things like if a new nuclear power plant is built or if a waste facility is built. They are the ones who ultimately oversee those construction efforts to make sure that things are being done in the proper manner to ensure public safety. So that is the primary job, the primary role of the NRC. Also involved in the process is the DOE. This is not the Department of Education, but rather the Department of Energy. The Department of Energy does a couple of things. They work on research and development primarily. In fact, there are a number of Department of Energy sites throughout the United States. One's not that far from here, Oak Ridge, Tennessee, about 350 miles away or so. And what is done at Oak Ridge and at Los Alamos and at some other places is they do direct research on nuclear materials, finding ways to be more efficient in our use of nuclear materials, and also trying to research ways to deal with the waste. Right now, the best scenario, the best case that we have for dealing with the waste is burying it underground in a concrete chamber. It's about as good as we can do. But the DOE oversees some other kinds of research and development in terms of not only trying to deal with the waste, but also trying to get new ways of energy. And so one type of thing that has been worked on for several years, most of our radioactive materials that we use for energy are uranium. Uranium is found in certain types of rocks, and through a process of enrichment, the uranium is used to generate energy by basically harnessing the nuclear binding energy inside of that uranium atom. And when we hit it with a certain kind of material, we cause it to burst, and that splitting of the uranium causes a large amount of energy to be released. Well, there's been a lot of research done in more recent memory that uses thorium, element number 90, which is 2 doors down from uranium, a naturally occurring material, and also the product of uranium when uranium goes through a nuclear decay that might have some utility as well. And so a lot of research has been done on thorium to see if thorium could be a useful feedstock because it's a little bit more bountiful, it's a little bit more common, and it is something that we do have as a byproduct of natural decay of uranium. So the Department of Energy does a lot of that kind of research. The Department of Transportation, our old friends, the DOT, they are the ones that oversee what happens when radioactive materials have to go from one place to another. So we already know about their placarding system. Those are the yellow the white, yellow, and black placards that say radioactive, the class 7s, but they also oversee other kinds of regulation with regard to that as well. EPA is responsible for establishing what we know as regulations in terms of how much you can be exposed to in a given amount of time, not only in the workplace, that's more on the side of OSHA, but just in your overall general everyday life. Probably one of the biggest missions of the EPA is about the encounters with everyday radiation. You encounter radiation on almost a daily basis. Kind of essential for us to live, the sun. Now, most of the really bad radiation gets blocked by our ozone layer. But we do encounter baseline radiation on almost a daily basis. Most of that coming from things like radon, which is a gas that is in the air in very, very trace quantities and can be found in certain types of ground materials because it's a naturally decaying product of radium, which can be found in the earth. So one of the areas where the EPA really does spend a lot of its focus is on things like radon testing. You know, when you go to buy a home, periodically throughout your tenure in living somewhere, getting radon testing is always considered a good idea because radon can seep through concrete and come in through the basements of your house, and it's radioactive and kind of nasty. And so just testing for baseline amounts of it and making sure that you don't have an elevated concentration of radon is an important thing to know. OSHA is responsible for establishing the exposure limits at the workplace. They also will make recommendations in terms of how much you're exposed to in a given amount of time and what kinds of personal protective equipment are required and necessary for different kinds of tasks in the workplace. Now, the primary thing that we will look at with looking at radioactive materials is the nucleus. So unlike chapters 4 and 5, where we really focused on the electrons and the things that those electrons were doing to make chemical bonds, in radioactive materials, the electrons really have no role in whether something is radioactive or not radioactive. Radioactivity is all about the nucleus. And so when we look at the nucleus, we understand that inside that nucleus, there are two primary subatomic particles. There are the protons. And remember from before that the protons have a positive charge. And we've got the neutrons, which really have no charge. Those are the two components, and those are that's what they do. So we've got protons and we've got neutrons. Now, recall also, going back now to chapter 2, when we have nuclei, the thing that ultimately determines whether or not an element is an element of carbon or an element of nitrogen is the number of protons in the nucleus. And so when we talk about nuclear stability for a given element, we know that the number of protons in that element is not going to change. The only thing that will change are the number of neutrons. And so what we have is the possibility of variability inside of the atom itself, to the point where if we have different numbers of neutrons, we will ultimately have different isotopes of that element. So an isotope just refers to, I've got two atoms, both of the same element. They both have the same number of protons, but they differ in the number of neutrons, and so they differ in the mass number. And so that's an important thing to note. And so one way that we identify those is that we can identify our isotopes by their mass number. So you may recall from going back a few chapters, we identified elements like carbon 13, and we compared it to carbon 12. Same element, different mass number, and a different mass number because there are a different number of neutrons in that nucleus. And so just to kind of reiterate that whole point, remember that there were two ways to describe an atom of a particular element. We obviously describe the atomic number. The atomic number is the number of protons in that nucleus. We can find the atomic number on our periodic table as the top number, that whole number at the top of the element box. Again, that's the number of protons in that nucleus, and that helps to identify what kind of element the atom is. Mass number, on the other hand, is not given to us on the periodic table. Mass number is individual for a given atom, for a given isotope, and it's the total number of protons plus the number of neutrons in that particular isotope. Mass number for any isotope is equal to the number of protons plus the number of neutrons. So let's look a little bit further. Every element on that periodic table has at least a couple of isotopes. Now, on average, elements will range from having about 3 isotopes, which is probably the most common, especially for the lighter elements. Some elements will actually have as many as 25 isotopes. Now, just because we have an isotope available for a given element doesn't mean that those isotopes are necessarily stable. In fact, very few of the isotopes among these that are being mentioned are stable. Most will undergo some kind of radioactive decay in order to get to a more stable form. The ones that are stable, however, will retain their structure. So good examples of these would be things like hydrogen 1, carbon 12, oxygen 16, and so on. These are stable isotopes, and these are the most abundant isotopes of the 3 elements that I listed. Now, there are other isotopes that exist for these elements that are not as stable. So take, for example, deuterium, tritium, carbon 13, carbon 14, oxygen 15, oxygen 18, and so on. These isotopes all exist, but all these ones here on the bottom are unstable. And when they are unstable, they will spontaneously react to form a more stable nucleus as a result. We call that particular phenomenon, when the nucleus breaks apart, as radioactivity. Now, radioactivity itself brings about with it a couple of key ideas. Results of radioactivity include a more stable isotope, plus a release of energy, and sometimes a characteristic radioactive particle. This isn't always the case, but usually the case. And so what's really scary about radioactivity is that in getting to a more stable state, the release of that energy and that particle can usually be what have pretty disastrous effects on our health. Because the energy release is usually of a high form. That high form of energy, when it interacts with our bodies, is usually what we call ionizing radiation, meaning that it'll strip electrons from our cells. And when electrons get stripped from the cells, they have a tendency to die or mutate or react. And usually the effects of any of those things have some kind of nasty health effect for us. And so, again, this happens with the unstable nuclei. The unstable nuclei are the ones that are ultimately radioactive. And so another name for their isotopes are radioisotopes, sometimes referred to as radionuclides. A nuclide just being a particular combination of protons and neutrons. Another way for saying an isotope, basically. So, as I said in the previous slide, these changes in radioactivity are not isolated events. When we go from a stable or from an unstable nucleus to a stable nucleus, the only thing that happens is not just that we get a more stable nucleus. There has to be an energy differential as well. The unstable nucleus has a lot of energy. The stable nucleus has less energy. To go from high energy to low energy, I have to get rid of some energy along the way. And that's what happens when radioactive decay occurs. That excess energy gets released, and it also usually comes with that particle. Now, there are some forms of radioactive decay where an electron ends up getting absorbed by the nucleus, and that absorption of the electron helps to stabilize the nucleus, but we still see a release of energy when that happens. Yes. Okay, so when we say that a particle is being emitted, we're talking about something tangible, something physical. Now, what is released can vary in size. So sometimes the particle that is released is kind of on the heavier side. Can be as big as basically a helium atom, which doesn't sound like much, but considering we're talking about an individual atom breaking apart, a helium atom coming off of a larger atom is fairly significant. In other cases, the particle that's being emitted is a lot more like an electron in terms of size. So relatively small, but if I eject an electron at high energy out of that nucleus, it can do some pretty considerable damage when it encounters other materials. So the particle, like I said, we'll talk about the particles here in a minute. They get about as big as that helium nucleus or about as small as an electron. But it's always particulate. It's always some sort of subatomic particle that's being thrown out there. Important term here for you, though. Half-life. You're going to see half-life as a part of, you're doing the radioactive materials lab today, am I right? So we don't know. Thanks for reading the syllabus, guys. Okay, it's either this week or next week that you're doing the radioactivity lab. One of the things that you're going to do is a half-life simulation. It's a website that I found that simulates what a half-life looks like. Basically, the half-life is this. Let's say I have a bundle of radioactive material. The half-life of that radioactive material would be how long does it take for half of that material to decay? Now, the kind of cool thing about this is that the half-life for a radioactive material is consistent, meaning that it doesn't matter how big this bundle of material is, the half-life will always be the same unit of time. So let's say that I have 100 particles over here, and it takes 5 days for that 100 particles to turn into 50, where the first 50 go off and decay, the remaining 50 are still here. It's going to take another 5 days for that 50 particles to turn into 25. It's going to take another 5 days for that 25 particles to turn into 12. It's going to take another 5 days for those 12 particles to turn into 6. Another 5 days for those 6 to turn into 3, and so on. Half-life for a radioactive material is independent of how much material you have. It's always going to be the same amount of time. And that's kind of interesting because it kind of goes against what you would think. You would think that the more stuff you have, the longer it would take for half of it to decay. Okay, if I have 100 things, how long am I going to have to wait for 50 of them to go away? Where if I have 2 things, I would expect that eventually one of them is going to decay. And that time it takes for one of the 2 to decay, it's going to be a lot shorter than it took for the 50 to decay. But it doesn't work like that. It's the same unit of time either way. So graphically speaking, this is what half-life looks like. So if I start with 1 kilogram of material and my half-life happens to be 1,620 years, which is a real half-life, mind you. Half of it decays away in that first 1,620 years, another half after another 1,620 years. I go down to an eighth after another 1,620 years. These long form half-lives are actually something that we use for a really common application of radioactivity, and that's something called radiocarbon dating. If you've ever heard of carbon dating for things like historical artifacts, or how we determined that dinosaurs roamed the earth about 65 million years ago, it comes primarily from this idea that every living thing has some carbon in it, and some of that carbon is radioactive. Now, not the nasty kind of radioactivity that can kill you, but a radioactivity that you have a small amount of in your body at all times. And as you're living, you flesh out and change out the carbon in your body on a regular basis. Well, when you die, you don't exchange carbon anymore. So whatever carbon 14 that you had in your body at the time, that's it. And it starts to decay away. And so you can figure out how old something is by comparing how much carbon 14 it has when you found it versus how much we expect that it would have been as a living being. And you can compare the two and figure out based on half-life how old it is. Now, when it comes to calculating half-lives, any kind of calculation I give you with half-life is always going to fall into a nice round number of half-lives. So if I tell you that 5 half-lives have elapsed, then you should understand that 1/32nd of the original sample is left. Basically, all that you do is you multiply the original amount by 1/2 for however many half-lives have gone by. And that's what you do to do that comparison. So you figure out how many half-lives there are, and you multiply that number of half-lives by the half-life of the material, and that tells you how much time has passed. All right, the last thing that we'll talk about today, and if you are doing the radioactive materials lab today, this is something that you will get to investigate, is that there are 3 different types of radioactive decays, 3 different types of ionizing radiation that come off of your radioactive materials. Again, this is natural decay. This is the kind of stuff that radioactive materials do on their own. This is not the kind of thing that it happens in nuclear power plants or nuclear weapons. Those are artificial types of decay. But natural decay comes in one of 3 forms. We either have alpha radiation coming off of it, beta radiation coming off of it, or gamma radiation coming off of it. Alpha radiation happens primarily for our heaviest of elements. So if you look on the periodic table, once you get past element number 83, bismuth, notice that on the periodic table, every single atomic mass after element number 83 every single atomic mass after element number 83 is in parentheses. And those that aren't, in particular thorium, protactinium, and uranium, those are elements that do have multiple isotopes that are not stable, but present in high enough quantities that we can measure them. After element 83, though, every single one of those elements is radioactive in some kind of way. So polonium, radioactive. Astatine, radioactive. Radon, radioactive. Francium, radioactive. Radium, radioactive. And you can go all the way through all the rest of them and get the exact same result. Primary reason that these are radioactive materials, whereas the others are not, is that the atoms are just too darn heavy to stay together. And so when we have atoms that are just too darn heavy to stay together, alpha decay is the primary means for them to get more stable. Because alpha decay is going to end up with them ditching an alpha particle. The alpha particle has an atomic number of 2 and a mass number of 4. And that sad little squiggly line, which I'll try to draw a little bit better, is the Greek letter alpha. Kind of looks like a little fish. The Greek letter alpha describes this particular level of radiation. This is the one I was talking about as being the heavy particle. Because with an atomic number of 2, we're talking about helium. Mass number of 4, we're talking about the most stable isotope of helium. The only thing that really distinguishes the alpha particle from the helium is that this particle has no electrons, whereas helium would have 2 electrons. And this particle is ejected at relatively high speeds compared to helium, what helium does kind of on its own. So ditching this heavy energy helps to make the big heavy isotopes a little bit lighter and a little bit more stable as a result. Because of their bulkiness, these alpha particles are rarely of concern to us, because since they are so heavy by comparison, they're relatively easily blocked. Things like your skin, your clothing, relatively not that dense materials can block the transmission of alpha radiation. Really, where we concern ourselves with alpha radiation is if alpha radiation managed to get on the inside of us, like we ingested an alpha radioactive source, then it could do some considerable damage to our internal organs, because those internal organs don't have the thick barriers around them like our skin does. Beta decay primarily consists of the ejection of negatrons. Negatrons are just kind of a way of describing electrons that are emitted from nuclei. In beta decay, the way that they look is like this. We'll have a 0, a -1 for the charge, and a Greek letter beta. This can also be depicted with an E for electrons. This kind of radioactive decay is a little bit more dangerous, since the negatron is not nearly as heavy as the alpha particle. When it gets ejected from the nucleus, it does get ejected at a considerably higher speed. And because it is that much smaller, small objects aren't sufficient in blocking their transmission. So your skin is incapable of blocking a beta radiation. It'll penetrate your first layer of skin and cause some pretty nasty looking kind of radiation burns, kind of similar to a really bad case of sunburn. However, your internal tissues are dense enough that they don't really go further than that first layer of skin. So for the most part, your internal organs and whatnot are relatively safe from beta radiation, unless, again, you ingest it in some kind of way. Now, with beta decay, there are some side processes that are possible. One of these is called the positron. The positron is essentially a beta particle that has a positive 1 charge instead of a negative 1 charge. A third process of beta decay, actually something called electron capture, where the electron is added to the nucleus of the radioactive material. And essentially what happens there is we turn a proton into a neutron by adding a beta particle to that proton. It essentially positive charge plus negative charge annihilate each other, and we get a neutral particle as a result. For beta decay, usually what is the driving force by these is the neutron to proton ratio. When the neutron to proton ratio is off, it's not the right ratio, that's when we tend to see beta decays. And they'll come in one of these 3 forms. The last of these is gamma decay. In gamma decay, we have just a generic form of electromagnetic radiation that is given off. So there is no particle with this. There is no gamma particle. We will sometimes see gamma radiation shown as a gamma ray. The gamma ray looks like this: 0 mass, 0 charge, Greek letter gamma, lowercase gamma, given there. This is the most dangerous form of decay. Because there is no particle, it's all energy, all radiation. And as a result of having no particle to kind of slow down the energy, when the energy gets to you, it's at very, very high energy rates. There's no particle to slow it down. So it tends to just kind of pass right through you. And as it passes right through you, it has the capability of ionizing pretty much any matter that it encounters. And that's why it is very, very dangerous as a result. In order to block gamma radiation, you need either several inches of lead or a number of feet of concrete as a barrier. That's the only way that you can actually trap that gamma radiation from going any further. It needs to be something incredibly dense, and there needs to be a lot of it. So that's where we'll stop for today.